Hello, my name is Locke. Today we'll go over key ideas and results from our paper, Differential Property Prediction, a machine learning approach to experimental design in advanced manufacturing. This work is a collaboration between a team of material scientists and data scientists. I would like to thank everyone on our team for making this work possible. The motivation for our work comes from the need to help material scientists leverage existing data to better design future experiments for shape. Shape is a solid phase processing technique that can extrude hard metal and alloys at cheaper costs compared to conventional method. During a shape experiment, the material scientist can control different processing parameters to generate material with different mechanical properties such as ultimate tensile strength, yield strength, and max load. Currently, there is no physical model for shape. Experiments are being guided through trial and error. Our goal is to train an ML model that can suggest good processing parameters that produce good property to help material scientists design their next experiment. In this work, we introduce a framework called Differential Property Classification, or DPC, where we can frame a regression task into a classification task. Through this framework, we can make statements such as Model A correctly classify the better processing parameter 90% of the time. Such a statement can help material scientists understand the ML performance better and can be a good tool to help them design their next experiment. In DPC, we have three classes. Class 0 is if processing parameter A produces better property than processing parameter B. Class 1 is if the reverse is true, and Class 2 is if processing parameter A and B produce the same amount of property for up to a certain tolerance. We want to produce a good model that has high accuracy in predicting the processing parameter that yield the better properties. Our framework is architecture agnostic, so you can select a particular architecture that best fit your dataset. In this work, we explore XGBoost and a feed-forward neural network. You can try other architecture that would work better for your particular case. Our framework also supports different backbones for different model type. We explore direct regression, difference regression, and classification prediction. Direct regression, we take input from processing parameter A, produce an output, take input from processing parameter B, produce an output through a regression model. Their difference is being used for the classification we outlined earlier. In difference regression, we take A and B at once into the regression model and try to regress the difference between output of A and B as we did earlier, but instead of doing it one by one, we do it in one step, and the result is used to produce the classification. In classification prediction, we produce the classification that we outline here directly without going through the intermediate step. We found that classification prediction outperformed the other two methods on out of the three physical property. Please review our paper for more detail. Finally, we showed that the DPC framework can still perform well in extremely low data regime where only a few training samples are available. This graph, we only have 3 to 5 experiments provided to the model, and we've shown that DPC performance is still reliable in the 80 to 85% in terms of accuracy, even though have access to very limited amount of data. We hope that through this simple framework of translating a regression into a classification problem, we have provided material scientists and data scientists with a new way to gauge their model effectiveness for advanced manufacturing process, and which in turn can help material scientists build better materials in the future. Thank you.
Hello, my name is Joan Song, and today I'm going to be talking about anomaly segmentation network using self-supervised learning paper. The presentation outline is as follows. Anomaly segmentation, which localizes defective areas, is an important component in large-scale industrial manufacturing. However, most recent research have focused on anomaly detection. This paper proposed a novel anomaly segmentation network that can directly generate an accurate anomaly map. using self-supervised learning. Therefore, compared to the existing method of indirect generating anomaly maps, the proposed method generates a more accurate anomaly map. Recent anomaly segmentation method generates an anomaly map using existing detection algorithm without directly generating anomaly map. Therefore, as shown in figure B, C, and D, the anomaly map of these methods cannot generate an accurate anomaly map. The proposed methods use hard augmentation, adversary learning, and coordinate channel to generate an anomaly map directly. Therefore, an anomaly map very similar to GT mask is generated as shown in figure G. The proposed Anomaly set is a holistic approach which incorporates three techniques: self-supervised learning using hard augmentation, adversary learning, and coordinate channel concatenation. The proposed method uses hard augmentation and copy-paste to generate synthetic anomaly data and GT mask. Hard augmentation refers to generating sample shift away from the original sample distribution. Therefore, as shown in figure, we use three types of hard augmentation: rotation, firm, and color jitter. Each augmentation is applied with 50% chance. Then, by copy-paste, the augmented data is pasted into a random region of normal data to generate the synthetic anomaly data and corresponding mask for segmentation. To improve the generality for various anomaly data, it is important to find normal region distribution accurately. Therefore, ONSEG utilize masked reconstruction rules that use reconstruction rules only in normal region to run only the distribution of normal region. Also, since the discriminator input a pair for an input image and its DT mask, the discriminator and generator can focus on normal region distribution. Therefore, anomaly region cannot be reconstructed well, and the detail of anomaly map can also be improved. To provide additional location information, we use a coordinate vector inspired by code combo. We generate bankable metrics that are normalized from -1 to 1 for x and y axis, respectively, considering the coordinates. Then we concatenate these metrics with the input image as channel. As shown in table, Onosega performed the conventional state-of-the-art such as patches VDD, spade, and copy-paste by 1% AURC square. In particular, patches VDD and spade achieve AURC score similar to Onoseg in the evaluation of ARC, but have low IOU score than the proposed method. Also, Onoseg could improve generalization performance for normal region and show that our model is robust against thresholding changing compared to existing method for extracting anomaly score in the indirect method. This paper presents a novel anomaly segmentation network to directly generate an anomaly map. The proposed ONSEG is a novel approach which incorporates three techniques: self-supervised learning using hard augmentation, adversary learning, and coordinate channel concatenation. Experimental results on the MVTAG dataset using AURC and IOU demonstrated that the proposed method is a specialized network for anomaly segmentation compared to the existing method. Thank you for listening to my presentation.
Hello, my name is Nathan Brown from Clemson University's Department of Mechanical Engineering, and the title of my presentation is Deep Reinforcement Learning for Engineering Design through Topology Optimization of Elementally Discretized Design Domains. I want to jump right into the objective of this presentation, which is to use deep reinforcement learning to design optimal topologies. The goal of reinforcement learning is to train an agent to complete a task within an interactive environment using feedback rewards. The mathematical framework of reinforcement learning problems are defined as Markov decision processes. Now, there are four key elements of a Markov decision process. These include the state and action space and the value and reward functions. We believe that if these four components of the Markov decision process can capture critical information about a particular design domain, then a reinforcement learning agent will be able to learn to produce optimal designs within that domain. The particular design domain we are interested in is topology optimization, which aims to optimally place material within the domain based on certain objectives and constraints. Breaking down the four components of the Markov decision process, we start with the state space, which represents all the observations the agent may experience within the environment. And this is formatted as a three-layer n-by-n array that captures critical information about each element in a given topology, including the stress distribution and location of bounded and loaded elements. The action space defines all potential actions the agent could take. We test the agent with sequentially removing elements from a starting solid block topology until it takes an illegal action or produces an optimal topology. Therefore, the action space includes the ability to void any material block. Illegal actions were categorized as trying to remove an element that would lead to an infeasible topology, such as removing a bounded or loaded element, or removing an element that would lead to a non-singular body. The reward function was set to mimic the multiple objectives of the compliance minimization topology optimization problem and assigns the agent more reward for removing elements that lead to a minimal increase in strain energy. Finally, the value function uses a double deep Q-learning algorithm to predict the value of removing each element given the current observation. The value function is built on a simple four-layer network built entirely on convolutional filters. This network takes the current observation as the input and outputs the predicted value of removing each element. The agent voids the element associated with the highest value, and in turn produces a new topology and corresponding observation. It should be noted that this network can be used on any size topology because convolutional filters are not size dependent, and therefore this network is not limited to the 6x6 representation shown in this slide. Now that we successfully defined the four components of the Markov decision process, the next step is to train and test the agent on designing topologies. The agent was trained by designing 6x6 topologies with randomly generated boundary and loading conditions. To improve the topology complexity and design practicality, we introduced progressive refinement during the testing phase. This allows us to sequentially increase the topology detail. The design process, which is shown in Figure 4, shows the agent starts by designing at the 6x6 topology size until an intermediate user-specified volume fraction is met. At that point, the equivalent topology at the 12x12 size is produced, and this process is continued and repeated at the 12x12 and 24x24 topology sizes, until a final volume fraction is satisfied at a 24x24 topology size. It should be noted that for all three topology sizes, the same convolutional neural network that was only trained on 6x6 topologies can be used because, again, convolutional filters are not size dependent. Upon introducing this progressive refinement approach, we tested our method on a series of user-specified load cases. In this slide, we show the proposed design solutions of the agent under various user-specified load cases. We have included the intermediate 6x6 and 12x12 topologies and the final 24x24 proposed design solution. The two examples with the green stars are unique because they prove that the agent is generalizing and not just memorizing. Remember, during training, the agent only experienced examples with a single loaded element and two bounded elements, whereas these two starred cases introduce multiple loaded elements. The agent is therefore generalizing to unforeseen load cases while still achieving optimal results. We've also included a comparison of the design solution and final strain energy between the reinforcement learning designer and a traditional gradient-based topology optimization solver. The results show that the reinforcement learning agent does equally well in designing these topologies. In conclusion, we show a deep reinforcement learning agent can learn generalized design strategies to design objective-based topologies given a multi-objective reward function. The agent was shown to generalize to unseen load cases and not just memorize experiences from training. We hope that this work takes an important step in validating deep reinforcement learning as a vital engineering design tool that should be incorporated into other design domains. I thank you for your time, and I look forward to answering your questions.
Hello everyone, my name is Song Wang and I will introduce our work to you today. In our paper, we propose an intelligent system to give user recommendation of DC to DC convert topology, optimal parameter settings, and expected power efficiency. This picture shows the workflow of our system. It's a machine learning enhanced automated circuit configuration and evaluation of power converters, or we call it ML accept. The user needs to give the inputs of their desired parameters to this system, such as the input voltage, output power, isolation condition, and then the system will give corresponding recommendations. The system consists of 3 modules: a decision tree, a reinforcement learning system, and a physics-based simulation model. The decision tree takes specified parameters as input and gives recommendations on which convert topology should be used, such as block topology, both topology, forward topology, and so on. Once we have the recommended topology, then we use the reinforcement learning model to search for the optimal parameters with respect to the power efficiency. For each DC to DC convert topology class, we systematically run its physics-based simulation model at every grid point in the parameter space to generate measures of power efficiency. The dataset is then used to train a deep neural network as a surrogate model of the simulation model for the topology class. The neural network model is then used by the reinforcement learning model to estimate the power efficiency of a DC to DC converter with any sample of design parameters in the defined space. Okay, that's it. Welcome to read our paper or poster for more details. Thank you.
Hi, I am Rafael Bisturi. I am postdoctoral associate in the mathematics department at MIT, and today I am presenting about data efficient training of physics-enhanced deep surrogates. What is a surrogate model? It is a learned model that fits a particular outcome of a partial differential equation, which I will call PDE. It is not a solver that will compute the solution to the PDE, but rather a data-driven model which will fit a particular property of the PDE solution. For example, in optics, where the PDE is Maxwell's equation, this surrogate model is fitted to predict the complex transmission through this structure based on the parameters of the geometry, here the width of the different rectangles, there are 10 of them, and the frequency of the incoming light. At evaluation time, since a surrogate model does not solve for the PDE solution, but rather evaluates a fit, surrogate models are orders of magnitude faster than PDE solvers. For an application like this in optics, a typical speedup would be 10,000 times faster for 2D simulations and 1 million times faster for 3D simulations. In practice, again in optics, this surrogate model is used in conjunction with decomposition methods for very computationally challenging simulation problems, such as computing the light scattered by a metasurface. If you are interested, please refer to my previous work in Optics Express. But there is no free lunch. The fast evaluation time comes at the cost of generating a lot of training data, which involves computing PDE solutions many times. Data generation certainly is really the bottleneck of high-dimensional surrogate models. Now I will focus on a neural network surrogates, which I call deep surrogates. And in the past 2 years, I studied 2 questions to improve the data efficiency of deep surrogates. The first is, how can I use the feedback from the surrogate model as it learns to find the best set of training points for the best accuracy, which I answered with an active learning algorithm published in NPJ Computational Materials, and which can save an order of magnitude of data generation. But today I will focus on this second question. How can we leverage field knowledge inside the surrogate? This work was published on arXiv at the end of last year. We want to fit the complex transmission computed by an accurate solver, symbolized here by a picture of James Maxwell. And the idea of the physics-enhanced deep surrogate called PEDS is to combine a neural network generator with a low-fidelity model, symbolized by a cartoon of James Maxwell. In itself, the low-fidelity model is very inaccurate, with an error of 100% or more, but it contains the knowledge of the physics, Maxwell's equation, conservation laws, and it computes much faster than the high-fidelity solver. The surrogate model takes in the same geometry as the accurate solver, and inside PEDS, there are 2 channels. One is a field knowledge-based transformation of the input to an input of the low-fidelity solver. And the other channel goes through a generative neural network that will alter this low-fidelity solver input. Trained end-to-end, the neural network generator finds the input to the low-fidelity model that will result in the same complex transmission as the computationally costly accurate solver for Maxwell's equation. This type of surrogate model is about 10,000 times faster than the costly Maxwell's equation for 3D simulations. Here I am presenting the fractional error on the test set with respect to the number of training data for this optics surrogate that I presented. I compare the result of PEDS combined with my active learning algorithm to a neural network only baseline and an improved baseline that uses active learning as well. The improvement is dramatic and potentially asymptotically faster. I am very excited to be presenting here, and I'm open to collaborations. Please contact me if you want to use this framework for your own physical systems.
Hello everyone, my name is Ho-Gun Seo. I'm really honored to present our study at this AAAI Adam workshop. Our members are me, Simyoung Liu, Jiyoung Lim, Jungwon Seo, and Yongkyun Liu. What I propose today is Quantile autoencoder for anomaly detection. Okay, let's talk about it. I think you are familiar with anomaly detection, which is a task that distinguishes anomalous cases in a collection or data stream. It has been widely used in diverse applications. As you know, in industrial field, we use anomaly detection to find something different or unusual in signals. Autoencoder is a very good tool for anomaly detection. Actually, it's a neural network trained to reconstruct an input into its output identically by training the model to ignore noise features. Autoencoder is also famous for dimensionality reduction. After autoencoder is fitted normal dataset, abnormal data results in larger reconstruction error than normal data. So if the reconstruction error of the some data are larger than threshold, we can regard them as anomalies. As you can see, the anomaly detection by threshold can be clearer as the reconstruction error distributions or anomaly scores between the normal and abnormal are far away from each other. Usually we use the mean squared error of the difference between the input and output as the reconstruction error, where the difference generally follows a zero-mean Gaussian distribution. Let's think about a case that has multi-channel signals, just k channels. Ideally, we can assume that the difference of each channel is independent and identically distributed. If we consider multivariate case of the KIID Gaussian normal random variables, the distribution of the mean squared error follows chi-square distribution, which is a special case of gamma distribution with the following parameters: gamma with k over 2 and 2 sigma squared over k. As you can see figure on your right, the variation, I mean the width of the mean squared error distribution become narrow according to the increase of k. So if we get narrower variation, I mean the width of the error distribution for the normal data set than the abnormal data set by increasing k, the separation between the normal and abnormal can be more obvious. In other words, it can be very beneficial for anomaly detection. There is a very important issue to handle multivariate variables in anomaly scoring. We need the orthogonalization of the scaling of our signals to guarantee the IID condition. So for that, we use the Marlon distance metric to match the range of the k error terms in this study. We mentioned increasing k is beneficial for anomaly detection. Right. However, still there is a remaining question. How to increase k? Yes, our answer is to adopt data uncertainty, also known as aleatory uncertainty, in anomaly scoring. Let's think about two cases. The first case is that normal data has small variation. The other case is that normal data has large variation. Regardless of variation, the autoencoder produces same outputs, so there is no possibility to adopt data uncertainty with the only autoencoder. So we thought we could increase k if we train the model for not only the mean value but also the data range of the normal data set. So we proposed Quantile autoencoder QAE for anomaly detection. The QAE outputs the lower, upper, and median quantiles. So finally, the anomaly score is derived from the reconstruction error as well as the range of the lower and upper quantiles as a data uncertainty term. In other words, aleatory uncertainty term. In order to train the data uncertainty term, the pinball losses are used to predict the lower, upper, and median quantiles. Since out of range reconstruction between the lower and upper quantile results in large losses, the model can predict optimal quantiles by minimizing the losses. To verify the effectiveness of the QAE, we compare the performance with the AE of RAPP. For this, we use same backbone of AE in RAPP. As you can see, AQN with the MSE show the best performance in most cases, especially in sensor-related datasets. As you can see, QAE show clear separation of the reconstruction error distribution between the normal and abnormal. Also, for various kinds of dataset, we compared performance with diverse models. As you can see, QAE showed more robust and superior performance compared to other AD methodology. So far, we introduced the proposed Quantile autoencoder for anomaly detection. As you saw that, additionally adopting data uncertainty is effective in anomaly scoring. For this, orthogonalization and scalings are recommended.
Hello, my name is Yain Park. Our paper topic is parallel attention network using vector with high correlation with labor for remaining useful life estimation. And I'll start my presentation. The outline is as follows. Prognostic health management is effective health management technology that monitors the status of equipment or mechanical systems in real time using sensors in the operation and maintenance phase, the diagnostics to catch failure signs, and prognostics for remaining useful life. What many users expect from a PHM solution is to know when a system will fail through prognostics, so remaining useful life estimation is an important in PHM. The remaining useful life is abbreviated to ROR. ROR estimation method is largely divided into physics of failure-based degradation model and data-driven approach. Among these two methods, we took the data-driven approach. It relies on historically collected data and attempts to derive models directly from the data for ROR prediction. Existing ROR estimation methods are classified into single, sequential, and parallel structures according to their structures. And recently, self-attention mechanism-based methods have been proposed. However, self-attention calculates the correlation of all sequences for each sequence. High computational cost is required, and it is difficult to verify features directly related to the actual ROR. So we propose a new method to solve the limitation of self-attention. Our contribution is as follows. We propose a novel attention network. The proposed attention network is constructed in parallel in the temporal and spatial dimensions. It can easily identify the spatio-temporal time series affecting the ROR. The proposed approach has the best performance, and its performance variation is the smallest for its dataset, so it is robust to data characteristics. The proposed network consists of 4 substructures: a time-oriented attention network, feature-oriented attention network, bidirectional LSTM network, and fusion networks. A description of each subnetwork is on the following pages. In our attention network, an intermediate prediction process is newly designed in the middle of the attention network process. Through the intermediate prediction process, a vector with high correlation with the ROR is trained. Then the learned vector is an input as a query to the scale-product attention process. Therefore, the key can determine the correlation with the query, which is a vector representing the ROR, so that the context vector including the correlation information between the input data and ROR can be obtained through the operation with the value. The proposed attention network is CNN-based and does not consider temporal information between data. Therefore, the bidirectional LSTM is used as one of the 3 path parallel networks to use temporal information that cannot be handled by the attention network. The fusion network concatenates the outputs of the 3 path parallel networks and outputs the predicted ROR value. The proposed method achieved higher performance in FD1, FD2, FD3, and FD4 than the state-of-the-art method. And the proposed method has proved to be the most robust model for the dataset characteristics by remarkably narrowing the performance gap. We performed experiments on the prognostic challenge dataset to provide additional results of the proposed method. We proved the superiority of the proposed method in both datasets through performance comparison. We proposed attention network guided by vector highly correlated with label, and the effectiveness of the proposed method was shown through various experiments. In the future work, we'll consider a real-time test environment to demonstrate the proposed approach in a real manufacturing environment. The references are as follows. Thanks for listening to the presentation.